Yeah. Hello. How are you? I'm Ryan. Nice to see you again. It's day 7. Doing Advent of Code. Sorry, I have to come up with a new way to pop out into the video every day. I don't know why I decided it's my thing. It's just what I do now. But we are a week into Advent of Code. If we finish today, we will have done a week straight of Advent of Code problems in Elm. I'm so excited. I don't even have Ellie open right now. But yeah, so if you haven't seen the previous videos in the series, Advent of Code is a month-long, like December code challenge thing, where every day, every 24 hours, they release a problem with 2 parts. And we have been using Ellie. Um, this is kind of like a code pen editor for Elm. I'm gonna do some CSS stuff. You don't normally see me doing this, but this is, I do have a template over here, but I'm too lazy. This is just some CSS stuff that I've got going on here. I think I do font family monospace. And then I do some, I do font size 125% so that the text is a little bit bigger. But anyway, that'll make everything monospace. And let's just delete all this confusing code and get some stuff printing on the screen here. Text. Hello. Oops. So this is Elm. And we so far have solved 6 days worth of these Advent of Code problems in it. I haven't seen day 7, so I start all these videos. I just click on it, and we try to do the problem together, and I'll just talk you through kind of how I do it. So if you're new to functional programming, this is for you. Cool. All right, let's just dive in, and let's see what our elves are up to today. They're like trying to collect stars because they're in a jungle. I still don't really know what's going on. Okay, day 7, no space left on device. You can hear birds chirping and raindrops hitting leaves as the expedition proceeds. Occasionally, you can even hear much louder sounds in the distance. How big do the animals get out here anyway? The device the elves gave you has problems with more than just its communication system. Try to run a system update. System update, please, pretty please, with sugar on top. And you get error, no space left on device. Perhaps you can delete some files to make space for the update. You browse around the file system to access the situation and save the resulting terminal output, your puzzle input. For example, whoa. The file system consists of a tree of files, plain data, and directories which can contain other directories of files. The outermost directory is called slash. You can navigate around the file system, moving into or out of directories and listing the contents of the directory you're currently in. Within the terminal output, lines that begin with $sign are commands you executed, very much like modern computers. CD means change directory. This changes which directory is the current directory, but the specific result depends on the argument. CDX moves in one level. It looks in the current directory for the directory named X and makes it the current directory. Dot dot moves out one level. CD slash, switches the current directory to the outermost. So that's like the root. And then ls means list. It prints out all the files and directories immediately contained by the current directory. 123 ABC means the current directory contains a file named ABC with size 123. dir xyz means the current directory contains a directory named xyz. Given the commands and output in the example, you can determine that the file system looks visually like this. So if we cd to the root and we list, we get an A folder, a b.txt, a c.dat, and a D folder. So right at the root, we see an A folder, a btxt, a c.dat, and a D. Cool. We cd into the A folder, we'll see that there is an, if there is cd into the A folder, we'll see there's an E folder, an F file, a G file, an h.lst file. Cool. So files might not have extensions, but they'll still be files because they don't start with dir. Okay, great. So given the commands, you determine that this looks like that. I'm sure if we kept following it, that's what we'd see. Here there are 4 directories, slash the outermost directory, A and D, which are in slash, and E, which is in A. These directories also contain files of various sizes. Since the disk is full, your first step should probably be to find directories that are good candidates for deletion. To do this, you need to determine the total size of each directory. The total size of a directory is the sum of the sizes of the files it contains, directly or indirectly. Directories themselves do not count as having any intrinsic size. Total sizes of the directories above can be found as follows. Total size of directory E is 584 because it contains a single file, I, which is size 584. Directory A has a total of 94,853 because it contains files F, G, H.lst, plus it includes file I because E is inside of I. So all these numbers add up to that 94,000. Okay. Directory D has a total size of, that's a lot, 24 million. The outermost directory contains every file. It's a total size of 48,381,000. Okay, cool. All right, to begin, find all the directories with the total size of at most 100,000. Then calculate the sum of their total sizes. An example above, these directories are A and E. The sum of their total sizes is 94,000. A process can count files more than once. Okay, got it. Find all the directories with the total size of at most 100,000. What is the sum of the total size of those directories? Dang. Okay, this is going to be intense. Yesterday we did in like 15 minutes. I have a feeling this is not going to be the same. All right, so how we start all these videos is we will take this sample puzzle input and we're just going to put some comments down here. And then we're going to have the puzzle input available as a string. So in Elm, we can just make values like this. And then multi-line strings in Elm use these triple quotes. So we're going to do that. And then what I want to do is I want to just call string.trim, which will get rid of the new lines here. So it'll make it easy to read this. And all we're going to do is we are just going to take that puzzle input and we are going to pass that into HTML text. So what you'll see is this is the string that we have, but to make it so that we can print anything, we're going to make sure that we turn this to a string so we can debug it on the right. So one step at a time, let's just dive into this and see what we need to do. So I'm going to start by breaking up each of these lines into their own contained thing. So here you'll see each line. Here is an element in this list. So now we've got this list of strings. And we need to know the difference between commands, and we need to know the difference between like responses. Let's kind of convert these strings into something a little bit more structured that we can work with. So to terminal line. So I'm going to make up something called a terminal line. And this is going to describe the stuff that we kind of like parse out of the string. So it's either going to be a command, which is going to either be change directory. And then this will say, what were the different options here? So it said change directory. So I either give it a name of a folder, I go up, or I go to the root. So I'm going to say change directory, and then call that. We can also call this change directory argument. So that's one possibility. We also have list files. So what they call ls? What does ls stand for? It means list. Okay. So list files command. So I'm going to just call this cd, or command details, or output. And this will be output details. Let's just start there. So when we see $/, so it's going to be cd, and then it's going to be there's just cd details, or ls. I think ls doesn't have any arguments, so I'm not going to include any arguments there. So I think Elm convention, we don't do like two capitals in a row like that. So a command will either be cd with the cd details, or ls. Sorry, I keep jumping back and forth. I think I'm just going to stick with this. I think this is easier. And then this is either going to be a file output, which has a size, which I think is just going to be an int, or it'll be a folder output. And I guess we could just like grab the name. It's going to be the name of the file, and this is going to be the size of the file. And then all I want to do here with CD details is cover the 3 cases we can be in. So we can say root or up one folder or enter folder that has some name. I'm just going to call this CD arguments. Okay, so what we need to do is we need to make a function called toTerminalLine that takes any string and it returns a terminal line. The problem is that this could be total gibberish, in which case we might not get a valid line back. So we're going to make toTerminalLine return a maybe, and in the case that we don't understand the line that we're given, we're just going to return nothing. So maybe is Elm's way of kind of throwing away information. And then in order to kind of only keep around the ones that aren't nothing, we're going to add a filter map here. So in the previous videos, we kind of covered that in more detail. But yeah, let's dive into this and see how we do. So I'm going to start by saying string.words. So if you use Elm's built-in string.words function, what that's going to do is that's going to break apart each line by its spaces. So we're going to get each argument one at a time. So in this example, we're going to be able to pattern match and say, all right, if we get $, we get CD, and we get slash, then that must be just CD. So CD arguments, we're going to give it the value root, and then CD with that is going to be a terminal line, and then we use just to make a maybe terminal line. So we can do the same strategy here. Maybe this won't be so bad. We'll see. This one is CD up one folder. So a common pattern you'll see when you're doing functional programming, especially with Elm, is, or I guess my only real like true experience like doing something in production is has been with Elm, is taking like the crazy raw input from the outside world and trying to like define like a data structure that'll be like easy to use later. So this is just going to be CD enter folder, and this will have the name of the folder. We're going to put it in a variable called name. So name here and name here will be the same. If I call this X, this would be X, and that would be whatever the whatever that variable is. Great. And then if we see $ls, that's going to mean it's just ls. That's all it is. And then if we see 2 arguments, this is going to be either size or, well, I guess we can just say dir, right? So in this example, like dir D or dir A, that's always going to be a folder. So this will be the name of the folder. This will be just folder output, and then we're going to say name equals name. And then finally, we're going to have this case, but this is going to be size. And keep in mind that string.words gives us a list of strings. So even though this is technically a number, this size here is still going to be a string, just like name is. So what we need to do is we're going to need to check to make sure that string.toInt and that size string succeeds. So if we successfully get like a size integer back, then it'll be a valid file. And then in that case, we can say size equals size int. And so I could have called this size. I just wanted to call it int to distinguish it from string and let you know that we don't want to deal with the case where, let's say, someone had chicken. Chicken b.txt is not valid, so that would hit this branch. File.txt. Like if this is not a number, that's when we're going to hit this branch. So let me undo chicken before I accidentally leave that in. And then finally, Elm is really good about this, so let's pretend we forgot. But if I compile, cd enter folder. Oh, and we got to use parentheses here. Thank you. Elm's really good about handling the missing possibilities. So what we want to do is we want to make sure that that we handle the edge cases. I know that there's more possibilities beyond empty list. There's like all kinds. So what we want to do is just say if there's any other type of list, any other type of string pattern that we find, we're just going to ignore that, say it's not valid. So now all of a sudden we went from this, where it's all just like raw text, to something we can work with. So now the first command is cd root, and I'm just going to scroll down so we can kind of follow along with the input. So you'll see cd root, then you'll see ls, and then you'll see there's a folder output with the name A. Then you'll see file output with the name b.txt and with the size. So like as we're going through, now all of a sudden we have like values that we can actually do things with. So we're getting a little bit closer. So this first part was just parsing things to terminal lines. So to help you visualize this, we started with a string. That was our puzzle input. String.lines gave us a list of strings. And then when we used filter map with toTerminalLine, what it did is it gave us a list of these terminal lines. If we just did, let's type it there. If we just did list.map, this would give us like a list of maybe terminal lines, and you get a bunch of like justs and parentheses around here. So filter map helps get rid of that. Helps get rid of that extra like wrapping. It makes it a little bit easier to work with these values. Now we can just loop through it, and we don't have to worry about like the cases where we have an invalid input. And just to show you that our thing is filtering out invalid strings, if this was just lol, that's not going to make it into our final list. Whereas if we just did map, it would keep it in the list, but it would represent it as like nothing because it would end up hitting this branch, and we don't want to worry about these. So for our program, just gonna assume the input's always good, discard the invalid strings that we find. And then finally debug toString turns it back into a string so that we can print it to HTML. This is the signature of this function here. And Elm needs HTML to print stuff to the right, so that's what's going on. Okay, so we have all of our commands one at a time. What we need to do is now we need to like kind of like simulate like a terminal. So we need kind of like the state of the terminal after this. So this is all about parsing. Okay, so what we're going to do now is we're going to try to represent the state of the terminal. So if we have kind of like the model of like the current like state of the world, what we have is we have the folder that we're currently in. So that folder could be represented as a string or a list of directories if we want. So empty list could mean like we're at the root directory. What I think we want to do is keep track of that, and then we want to keep track of the files that we found. So as we go, we're gonna kind of add information. So just to kind of go through that process, what we're gonna do is we're gonna say cd root. That's gonna make sure that we set our folder to a list of strings. So initially, our folder is gonna just be basically, we're going to assume we're at the root when the program starts. And then what's going to happen is we're going to need to go to the root, we do ls, and then with ls, this is like the output that we get. So if we see ls, we're going to start recording for this folder what we find here. So we have name equals a, file output. Yeah. So we have this folder, we have this file, we have this file, we have this folder, and then we hit another cd command, so then we stop. So what we need to do is we need to keep track of, for a given folder, like what's the size. So maybe I will use a string for now. I think that's a little bit easier to read. Maybe it'll be harder to work with, but let's just go with the string for now to keep it simple. So initially we have this, and then I'm just going to call this entries. And what entries is going to be is it's going to be a dictionary where we have a folder path. So I guess we can call this a folder path. This is going to store a thing where if you give me a folder path, I'm going to give you a list of file system entries. So an entry is either, sorry, I've got some typos here. An entry is going to either be a folder, which has a name, or it's going to be a file, which has a size. So if we want, what we can do is we can say output, and then we can just say entry here. And so our parser can use the same type that we're gonna try to be storing at each spot. So initially we're just gonna have an empty dict, and I'm just gonna I'm gonna hit compile. We're gonna get some compiler error messages. Elm's really good at like reminding you what you still need to do. So if you're ever like halfway through doing something, the compiler is it's got your back. So we're gonna compile this. Folder path, it doesn't know what that is. Folder path is just gonna be an alias for string, so it's exactly the same type as string. I'm just gonna use that to help us read this type and understand like kind of what type of value goes there. And then folder output doesn't exist anymore. Now we have output, and then we have folder. So that should work. And then here we have output file, because remember we changed this to store entries, and an entry is either a folder or a file. So if we want, we could move this down here. The order of things in this file isn't important. Okay, cool. So this is kind of like the state of our app. And what we're going to do is we are going to use something called a list fold that's going to work through one at a time. It's going to apply a terminal line to kind of our model, and we're going to keep going until we're out of lines, and then we're going to return the final state there. So here, this is going to be handle terminal line. And then we're going to give it the initial value. So our initial value is going to be this init. And hopefully at the end of this, what we're going to get is we're going to get a model. So handle terminal line is a function that's going to take an individual terminal line. It's going to take our current model, and then it's going to return the new model. So the new model might have a different folder. If we ran cd, it might have different entries. If we saw like some output in the terminal. So all we need to do here is take our model and say, in the case where my terminal line is of cd and I've got root, what I'm going to do is I'm going to take my model, keep everything as is, except the folder is going to be slash. If I get cd up one folder, what I'm going to do is I'm going to make a little function that takes the current value for the folder, move up one folder. So we'll come back to that. Elm will tell us to implement that. If we try to run the program, it's going to be like, let's move up one folder. And then their other option for cd arguments was enter folder. So if we get enter folder and we have a name, what we're going to do is we are going to do folder, and then we're going to take whatever folder we're at, and we're going to assume a folder always ends at a slash. We're just going to put the name there and a slash there. So this would be like slash. If we moved in a folder A, it would be slash A slash. So that's kind of how we're going to model this folder path. Finally, if we get ls, we're not actually going to change the model if we do ls. The folder is already where we need it to be, and the ls itself doesn't add any entries. So ls is kind of going to be like a no op. It's not going to make any changes to the state of our thing that we're working through. If we ever get an output and it is a folder, that's going to have a name. What we're going to do is we are just going to update the dictionary. You know what? This actually doesn't really matter if it's a folder or a file. We're going to do the same thing in both cases. So let's take a look at dict.update and just make sure that this is the one I want here. So update is going to take in a key. So the key that we're going to store things at is the current folder that we're in. And then it's going to take a function that goes from maybe a list of entries to maybe a list of entries. And then it's going to take in the existing dictionary and return the new dictionary. So let's make that happen. So what we can do is we can say, let's take the existing entries, dictionary. I guess we could put this at the end. The key that we're inserting in is model.folder. This is going to be our updated entries, which is going to be a dictionary again of a folder path to a list of entries. So updated entries, entires, if I can spell, updated entries is going to take dict update. As the key, it's going to use the folder that we're in. And then what it's going to do is this is going to say add entry to list, something to maybe list. And then finally, we're going to take the existing entries as our input. Yeah, that's right. And then what we want to do here is we're going to update the entries to now be this new value. So if I hit compile, all the code here is right. It's just we're missing some stuff, and Elm's going to let me know what parts we still need to add. So move up one folder is a function we need to implement, where we take a folder path, which is just a string, and return a new folder path. So if I have some folder path, what we're going to do is we're going to say string.split / So we'll take the existing folder path. That'll be a string. We'll split on /, and then what we're going to do is we are going to drop the last item from the list. So what we can do is, I think the easiest way to do this is actually, we're going to do list.reverse, which is going to put the last item front. That way we can use list.drop. Let me see if I can use a list extra function for this. So I'm going to look up Elm list extra, because I don't want to do this whole reverse and unreverse. Last. And cons last. Well, okay, let's not worry about it too much then. All right, so let's say our folder path was /a/b/c, and we said we'd always end on ABC. So what we're going to have is this is going to be a list where we're going to have an empty string because we split on slashes. We're going to have A, we're going to have B, we're going to have C, we're going to have an empty string. Hopefully this helps you visualize what this weird code's doing. C, B, A is what we're going to get when we reverse it. If we drop 2 items from the front of the list, we're going to be left with just B, A. Then we're going to should I put an empty thing on the front? Sure, let's do that. We're gonna have fun with this. I need a list. So we're doing operations on lists here. I think list.append is not what I want, but we can use list cons. We'll use this as a function here. So this is a weird operator that just says put an empty string at the front of our list. So I'm intentionally doing the indentation like this so you can see what's going on. But basically this is going to put an empty string at the front of our list. We're going to reverse it one more time. So this is going to swap the order of our old list. Bear with me, we're almost there. And then we're going to join it back together with the slash. So by doing that, all these characters are going to get joined back together, and hopefully what we'll see is slash will get joined with A, will get joined with B, will get joined with that white space. And so if you give me this input, I'll give you this output. The question is, does this work when I do empty root? Because that's like kind of like the edge case. So let's take a look. If I split an empty thing on slashes, I should get one of these. If I reverse the list, I should get the same thing. If I drop 2, from that, I should get an empty list. And then I feel like this won't work because it'll, I feel like if I drop 2 and I have an empty list, and then I put this in the front, and then I reverse it, and then I join that back together, I think if I try to join a single thing, it's not going to work out for me. So all I'm going to do is I'm just going to say if folder path equals root, then we just return root. Else we're going to do this. So I think that's probably the easiest way to handle this case, rather than to try to make this algorithm generic enough to support both, or clever enough. Okay, so hopefully that helps. And then this, of course, is over here. Elm format will kind of move things around on us. But I think these comments work as we expect. So at a high level, we're almost there. We just need to implement this add entry to maybe list. So earlier we saw dict.update takes a maybe value. So the values for these lists are these list of entries. So initially when we're going through the list, we might not find a hit for that folder yet. This might be the first time we're adding something. But what we want to do is we want to say maybe list. In the case where the maybe list is of nothing, I guess what we can do is we can say we're always going to have these entries. List of entries. So if we don't have anything, that's fine. And then we always want to return something. So we're going to say just, and then we're just going to say entries plus plus. And then, yeah, we're just going to add our entry to the end of that list. I think that's it. I think this is the whole simulation. That was a lot. I know that was a lot to deal with. Let me see if there's anything I'm missing. Okay, let's see if it's right. So here I have this very hard to read structure here, where at the end of my simulation, I'm in the D folder. Let me see if that's true. So at the end, I CD and a D, I LS. And if you look, there's like keys for each thing. So here, this is kind of tricky to read. Let me just move this in a place where we can see it. So what we created here, add a bunch of lines. So this is what we scanned out of the list. Oops. So what we can do is we can say foo, and I think I can just Elm format all this. Oh, this is so great. Elm format's awesome. That saved me so much time. Oops. Except for when I did that. And then I like to do these just to get these to wrap. So this is what we got out of the programs. This is all this garbled output on the right. This is our final model. So this is what we got when we ran this first simulation. So let's take a look at the puzzle and see if what we have here is accurate. So far, it's saying that at root, we have A, B, C, and D. So at root, we have A, B, C, and D with sizes 14848, 8504. 14848, 8504. This is looking good. And then A has E, F, G, and H. A has E, F, G, and H. Awesome. AE, so the folder nested inside of A, just has I. And we can see here it just has I, which is a file. And then D has J, dlog, dext, and K. Finally, J, dlog, dext, and K. So this is awesome. This is all the hard, crazy stuff. Now we have a really straightforward data structure to work with, and all we have to do is just add up all the sizes for these entries, and then just report back which ones are less than 100,000. So let's do that. So here I have, in our pipeline, we have our model. What we're going to do is we're just going to use this .entries function to get us back this. So now we discard the folder information. Now we're just looking at our dictionary. And all we're going to do is we are going to get the values of this dictionary. So now it's just a list of these lists of entries. So at this phase, it's a list of entries. And so what we want to do is we want to, for each item in the list, we want to add up the total file size. So we're going to say list.map, find total file size. So hopefully at the end of this, we're going to get a list of ints, which is going to be like the list of like bytes that we have. So if we want, we can also make a type alias here called byte and have that just be a secret nickname. Not a secret really, but just a nickname for int. So if we wanted to define find total size, it could take a list of entries and it could return us an int. So for each of the entries that we get, we could say entries. We could say list.map, find size for entry, and we just sum up all those sizes. So how do we make find size for entry? Well, it's the same thing, it just takes a single entry though. It says for a given entry, how do we calculate the size? So if we have a folder, we don't care about the name. The sizes we're going to count as 0. And then if we have a file, that's going to have a size. So we're going to do that. So hopefully when we're done with this, what we're going to see is that this, will give us a list of numbers. So we'll have this, this, and this. And so finally, we're going to filter the list. Let's say is less than, was it 100,000? Is that the filter? So we're going to keep every item, find all directories, the total size of at most 100,000. So this is going to filter out the big ones, the big one here and the big one here. We're going to need to define that this function is less than. You give me a cap and you give me a number, I will tell you if it's less than that. So this is limit, and this is the number. If the number is less than limit, then that's true. I just kind of created this for readability. We could have done an inline less than if we wanted to. So we could have also done like num less than that. This has totally been the same. So we still will have a list of bytes at the end of that, but it's just going to be the ones we care about. And then finally, we're going to add up all those numbers and pray that we get the 94,437. $853. Just 54. 584. I think I missed something. Four, 8, 5, 3. All right, let's see what I did. I think I screwed something up. 94268. Output okay. Let me just make sure I have the right input here. Just make sure this is right. This is right. 94269,584. Total size of, oh, got it, that's right. A contains E, so you have to count it twice. Forgot about that. We have to include subdirectories, so that was my bad. The size of a folder isn't 0. It's the size of the folder inside it. So the name does matter. So if we want to find the total file size, it's not going to be, we're not going to discard this information. So let me just rewind a bit. Let's just delete this for a sec. So we left off with entries. So what I want to do is find the total size. So this will take this whole dictionary, give me an integer. So if this is going to be our dictionary, what we want to do is we want to size for entries. So the code we had before was pretty close, but the issue is it needs to be able to look up the values of folders inside of it. So I'm going to just kind of get this to a place where we're compiling again. So we get file size. Let's get right back to where we were. 0. Okay, cool. So what I want to do is I want to say for each item in this list. So I'm going to say items, I guess values, should be a list of entries. This is going to be dict.values. We used that earlier. We're going to run that on the dict. And then what we want to do is we want to list.map. We're going to find the size for each entry, but we're going to pass in, we'll do this in a bit, but we're going to pass in each value. So this here, we're just going to say this returns a list of events. That's okay. Okay, so this is where we left off, but there's something wrong with our calculation. This is what's wrong. So what we want to do here is we actually want to find the size for the entries with that specific name. So we need to take the folder's name into account, and we need to use the dictionary. We need to look into this dictionary and say, hey, can you give me the list of entries for that? So I can say entries in folder. It's going to be a list of entries. So how do we get access to this dictionary? Well, we just pass it right in. So we say, you need access to it. So I'll let you have access here. We could also use a let expression and just kind of embed both of these functions inside of this one, which might be a little bit less typing. I'm just going to do it this way to show you how to pass, how you can pass data in here. So dict.get at name, I give it the dictionary. If we don't find any entries, that's totally fine. Default, we're just gonna say that we found nothing, so empty list. So if you ask me for, hey, what were the entries for folder X, it's gonna be like, well, I didn't find a match, so there were none. We're just gonna have an empty list of entries in that case. And so what we want to do is we want to find the size for the entries in that folder. Get warmer. So find size for entries. Oh, and keep in mind that find size and entries also needs access to the dictionary, right? Because we passed it in here. So now I think these numbers are bigger. Let's find out. Let's see if we do our filter again. So now that we have this, stop filter. It's less than 100,000. Mess this up, but find out. So that list.sum. No, it's the same number. I don't think I'm doing this right. 5. So find total file size. Find the size for the entries in the dictionary. These are each entries. It used to be 0, but now it is. Find the size for the entries in the dictionary. Entries in the folder. Oh, this is the name of the shoot. This is just the letter E. This isn't the path. This isn't the file path. That's what it is. So it's not finding a match. So the difference is name, just to show you what I mean. Name is like E, but the file path needs to be this. So I need to be passing in the folder path itself. So instead of values, I think I'm gonna do instead of values, what I'm gonna do is I'm gonna say dict to list. That's gonna give me a list of folder paths with their list of entries. So what I'm gonna be passing through here is not just the list of entries. That'll definitely be part of it, but also the folder path. So if I do it this way, let me just format this for you. This might get me in trouble with the formatting. Okay. So what I'm going to do is I'm going to say that we do need to know the current folder path because we're going to append this new name at the end with a slash, and that's what we're going to look up for the file path. That's how we'll get this. So folder path. This will be a single entry. Oops. You know what? This one will just pass in the folder path. Pass in. This is still a single entry, and then this is the like the current folder path that we're in. So if I pass in folder path right here, that's gonna find the size for each entry. It's gonna give like a slash will be like this argument. So I'll call this the parent folder, just for the context of this function. And then what I want is I want the folder path to be a folder path. And I want that to equal the parent folder plus the name of the child folder plus a slash at the end, because we always trail things with a slash like we did right here. So that's what the value of the key is going to be. So when I take this and do this, call this, I'm also going to go into the nested folder for any subsequent queries. So hopefully what we'll see is 94269 becomes that that 98 value that we saw before. Let's see. So close. Okay, find size for entries. Boop. looks like. The only difference is how we passed in these arguments. 4853. I think this is going to give us that bigger number that we're looking for. Let's try it one more time. And when I say one more time, I just mean as many times as necessary. But 95437. 95437. Okay. So it worked on our tiny little program. Let me delete some of these comments. I'm going to save this, and then I'm going to copy the link so that it's in the description of the video below if you want to look through it. I'll leave this here just for visualization, but this isn't actually a part of the solution. This is just kind of like a thing that we have. So I'm going to go here, and I'm going to say Advent Code 2022. This is day 7, part 1. So I'll do that. I'll hit save. Do this, put it over here. And so I'm signed in Advent Code on my GitHub. So I'm going to get a unique puzzle input. This is going to be different than yours. So your answer will be different. But what we're going to do is we're going to take this bigger, scarier input with all these different folders. We're going to run it. And then we're going to see if this code works. Sick. Okay. Awesome. That would have been a nightmare if it didn't. But here we are. So part 2 is usually like a slightly different like challenge on top of that. We spent a lot of time really modeling the file system correctly. So I think that we're going to be in great shape for part 2, but I might be surprised. Maybe it's a crazy difficult thing that it's asking us to do, but we really like went all out, with this and like modeled like the terminal line commands, and we have like all these things. So if they add a terminal line, if they add like, you know, what we want to query from the file system, we have that all here, and I feel pretty good about it. So let's see what they throw our way. Let's see what curveball they've got. All right, now you're ready to choose a directory to delete. The total disk space available to the file system is 70, is that 70 million? 70. To run the update, you need unused space of at least 30,000. Okay, so the total disk space available is 70 million. I need at least 30 million. You need to find a directory you can delete that will free up enough space to run the update. The example above, the total size of the outermost directory, less the total amount of used space, is 48 million. This means that the size of the unused space must currently be 21, which isn't quite what we need for 30. Therefore, the update still requires a directory with a total size of at least 838.1165 to be deleted before it can. To achieve this, we have the following options. We can delete E, which is 584. We delete A, which is 94,000. E and A are both too small because we need at least 83. They're not free up enough space. However, directories D and / are both big enough. Between those, choose the smallest, increasing the unused space by 24,933,642. Find the smallest directory that, if deleted, would free up enough space on the file system to run the update. What is the total size of that directory? Okay, so now I think this goes back to this just goes back to where we were before we did the list filter. So choose the smallest, increasing the unused space by 24,933,642. So unused space. So I need to know the total space, and that's the root directory. So 70 million minus this is how much space, free space we have. Increase it to this. Find the smallest directory that, if deleted, would free up enough space in the file system to update. What is the total size of the directory that we delete? Okay, so we just need to do a little bit of math here. Let's make sure that we can follow this. So I'm gonna run compile. This gives us our answer from before. We're left here with find total file size. think it's reasonable to say that the maximum file size here, so this is going to be do part 2. So we're just going to add one more function called do part 2. I think this is going to be good enough, where we get our list of ints. And I'm not even going to worry about what we have. So list of ints comes in, and then we'll be back for this. I don't know what this is going to return yet. So what we have is these are going to be our folder sizes. We know that the total size is actually whatever the biggest number is, that has to be the root directory, because the root contains everything else. So our total size is going to be the list.maximum of all the folder sizes. So by default, that's going to give us a maybe int, because we could have an empty list, in which case the size would be 0. I don't want to deal with maybes, so I'm going to say that if our list is empty, our total size that we've taken up, so total space used, is going to be 0. So if there's no items in the directory, it's 0, which makes sense. And then we have our maximum space available, which the problem said that the maximum space available is 70 million. Minimum space required. So I'm just kind of breaking down like the English in the problem to just like the variables that we have. So this was supposed to be 30, just making sure. 30 million. We can also just probably copy these. That'll probably be a safer way to do it. Make sure that I didn't misread. Okay. So what we want to do is if this is the total space used, this is going to be we need to know the minimum amount to delete. So the minimum amount to delete is we need to have at least 30 million. So if the total space used minus the minimum space required, that'll tell us how much space we need. So I guess how much space we need. I don't know if maximum space available matters. I don't think it comes in the equation. Or maybe it does. Remaining space available. Am I overthinking this? Probably. It's very late, so I might be totally bricking my brain. How much space we need is we need the remaining space available. Remaining space available minus the minimum space required. How much, I guess this is like how much we need to delete. So, maximum space minus how much space we used, how much we need to delete is how much space do we have. I guess it's the minimum space required minus how much space we have. And then I think I want to just say, let's just start with this, the folder sizes, and we're going to filter at least how much we need. So earlier we said is less than. And this is basically going to be the same thing, except this is like the minimum that we want to have. It's kind of like our lower limit. And I want to know something that is greater than or equal to that minimum. So this is now returning to us the all things above that threshold. And then I think we just want to find the minimum. So we'll change the type to go from a list, maybe. So 249,33642. 33642 is the answer. Okay, so I think this is part 2. I think this is it. Let me change this to say part 2. Save this. These are all ints. I'll add these in. I'll add these in because I care about you. You matter to me. And if you know what these types are, then you're gonna have a better time trying to wrap your head around this. Find smallest directory. We delete. About that. I'll make that crazy big. All right, that's still good. All right, saving that. And then I'm gonna copy this link for the video description. And let's see if we got the answer. So copying this, going back over here. Drum roll. Paste in our crazy big program. And we get 1623571. Ho, 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 ho. We did it. That's a full week of admin of code, folks. So just saying, we're on a roll. If I do day 8, I will have gone farther than I did last year, but only time will tell. Yeah. So all the solutions and stuff. I know this was a lot. This was actually kind of a fun problem. It had a lot of steps. It had turning the raw strings into terminal lines. It had implementing how to like move up a folder, like how to like change directories. This was a pretty fun puzzle, and I'm happy with how it turned out. But yeah, if you're curious, if you want to check out the solutions, they're in the description below. I'll also have links to the Elm core docs, or the package docs, in case you're wondering how any of these functions work. List.sum. If you wanted to find out, why minimum uses a maybe instead of like always gives an integer, stuff like that. That's all going to be available. I'll also have links to Elm and Advent of Code. And that's it. Thanks for hanging out, and I'll catch you next time. See ya.